All right, we are continuing on topic 5. And then what we have done has been covering various components like a multiplexer, like a decoder, like an adder, and so on and on. And what we're doing now is covering an ALU. What is an ALU? ALU is a mixture of various components, various functions. Like it adds, it subtracts, it does this and that and all that. And specifically, what is an ALU? Well, it depends on your application. It's a piece of hardware that you can tell it to do several things. Some do even multiplications. So what I'm going to do is just give you a very simple ALU, and with this simple ALU that I'll be covering, I will show you or talk about the corresponding Verilog construct, which makes it easy to describe not only an ALU, larger components, and then I will use the ALU as the relatively large example of the Verilog construct that we are talking about, which is really an always a statement. So let's start with this. The ALU is described here, described as such. We have a circuit that, let me draw the symbol for ALU. This is how it's usually done. Okay, preferably balanced on the two sides. And then this has F1, F0, and these are the function inputs. And then it has an 8-bit A, it has an 8-bit B, and it has an 8-bit W. Some ALUs also have flags, like a carry flag, okay? Like a zero flag, like an overflow flag, like a negative flag, okay? I'm not saying that I'm going to do this in this particular ALU, but just giving you overall functionality. So these are called flags that are issued depending on the result of the ALU. So let's say this. The ALU that I'm designing is an ALU with 3 inputs, the 3 function inputs, F2, F1, F0. If F1, F2, F1, F0 is A plus B, it performs adding. If it's 0, 0, 1, multiplies A by 2, or actually shifts A one place to the left. And if it is 0, 1, 0, it puts the maximum of A and B on the output. If it's 0, 1, 1, it bitwise ends. This is bitwise ending, bitwise ORing. This is 2's complement. And then these two just take A, send it through directly, take A and complement it and put it to the output. A lot of times what happens is you have a multiplexer here that you perform various functions, hardware-wise I'm talking about. You perform various functions and those functions are done. For example, let's say you do the adding, you do the multiply by 2, you do the MUX, and then the inputs, let me do with a different color. So the inputs that go here and here and here and here. So the inputs are used for various functions, and then the multiplexer selects which one function actually goes on the output of the ALU. So there is really nothing very strange or very unusual or difficult about the ALU. It is a very common function, common hardware unit in processors, but then the implementation of it is easy. It's just what you have seen already, use of multiplexer and use of various components that you have already seen. Because it's easy, because it really doesn't require much. So I usually, when I want to do an ALU, I don't go in and do little components of hardware. Instead, what I do, I write it in a very behavioral fashion, something like, okay, if function is 000, I want the add result to get this. If function is 001, I want the output to get this, and so on and on. So and then behind all of these sayings, I know what kind of hardware I'm implying. Okay, so this is a situation that you know the hardware, and you just don't want to take the time to actually do the actual hardware. So you write the behavioral description. And then this kind of thing happens again. And as you go into more and more complex circuits, again, to do the same thing. You say, well, I know what the hardware is going to look like, but then I'm not going to spend a lot of time doing the hardware. I'm instead writing the behavioral. And the behavioral uses statement in Verilog called always statement. And then that's why I'm using Verilog to show you the properties or the construct called always statement. Okay, so let's talk about always statement. Okay, without going into the ALU itself, which I will in a few minutes, I'm going to cover the always statement using a much simpler example, and that's the multiplexer we have done. Let me go back to this multiplexer. It says I have a 2-bit select input, and I have I have 4 inputs, A, B, C, D. I'm going to select one of those and go and put that on the output. And then I have used assign statement. Remember, assign if S is need to do this correction. I've done this before, but it looks like when you make a mistake somewhere, it stays with you forever. So these must be 2 equals. Okay, so if S is 2 tick B 0, then A goes on the output, otherwise B goes on the output, C goes on the, and so on. And this is an assign state. Let me show you the assign state and how it looks. This is implying a function that has W as its output. Okay, I'm only talking about this. Okay, and it has A, B, C, D as input. It has 2 bits of S as input, and then S1 is 0, and then this function is looking at S1, S0, and based on that is going to put A or B or C or D on the output. Okay, this is assign instant, and we know that already. Let me say it differently. This is a box, a hardware box, a combinational box. Okay, a box with some gates in it, right? Because the multiplexer, it has some gates in it. And however I describe it, using gates, using primitive components like and, NAND, and all those, using an assign statement, or using the always statement that I'm going to show you how, no matter how you describe this thing, the way it functions, the way the representation, the Verilog representation of this box works is the following. This box, or the Verilog description of it, sits and waits for an event to occur on one of the inputs. Okay? So the reason I'm saying this, if this box is producing an output, and let's say the output is 0, and the inputs don't change, there is no point in doing any processing, right? There is no point in doing any processing if there is no event or no change on the input. So the box is the output is 0 or 1. And the inputs are something. Okay? And then the box is sitting quiet, just waiting for an event to occur on one of the inputs. As soon as an event occurs on one of the inputs, it says, well, maybe the output is not going to stay as is anymore, so let's perform calculation. In the case of a sign statement, the way it performs calculation is that it evaluates this right-hand side with the new value of the event on the input. Maybe A, maybe B changed, maybe C changed, maybe S changed. With the new value, it's going to process this statement and then comes up with a new value for W. That new value for W will be put into W, and then this statement goes dormant again. Okay? Why am I saying all this? We know this already. We even know this if I write this, let's say this is a multiplexer, right? If I write a, for now, let's do a 2-to-1 multiplexer, S0, A, B. This circuit works this way as well. See, if A is 0, B is 0, S is 0, all right, this is 0. And this is 1. Okay. And if nothing changes, there is no point in evaluating these gates. You wouldn't, right? If everything is the same and I tell you what's the output, then you say 0, right? And then if I ask you again what the output is, you say 0. If I don't change the input, you're going to give me the same exact answer every time I ask you. But if I say, what if, let's say, S changes from 0 to 1, or A changes from 0 to 1, okay? Then you say, oh, okay, let me evaluate this circuit. Let me propagate this change through this little circuit and come up with a new value. So unless there is an input change, there is no point in evaluating this circuit. Okay? The circuit by itself is not going to do anything. I can represent this circuit using a sign, using gates, and in both cases is going to function the same way. In both cases, it's going to function exactly the same way. In both of these cases, however I write it, the description waits for an input to change and then evaluate the output. And one other thing, in no case, if an input changes, your output never retains its old value. Okay? Maybe the old value is the same as the new value, but then the old value never retains. This hardware, no matter how you describe it, does not retain an old value. Otherwise, it would have been a memory. So, what I'm going to do is find a better way of describing this same circuit. Not gate, not assign, not Boolean expression, something that I can very nicely describe the behavior of it using if-then-else statements and all that. So far, I haven't shown you if-then-else statements in Verilog. If-then-else statement, case statements make you able to describe very complex descriptions. This is not a complex description, but nevertheless, I'm going to use those descriptions to represent this so we learn it. I'm going to use what is referred to as an always statement. Okay? For describing this. The always statement must correspond to this gate level circuit or to this assign statement. When I say must correspond to this, means that the always statement has to wait until there is an event on any of the inputs and then start processing. In order to make an always statement wait for an event on certain signals, I put what is referred to as a sensitivity list of the always statement following an @ sign inside parentheses. So I say A, B, C, D, S. The always statement is sensitive to these signals. Unlike interconnection of gates or an assign statement or a Boolean expression that is describing the multiplexer that are concurrent statements, okay, and there's only one statement, they just wait for the event that occurs and then they perform what they're supposed to be doing. Always statement is also a concurrent statement on the outside. But the always statement, the good thing about it is within the always statement, between its begin and end, everything happens procedurally. That's what the key thing is. See, we think procedurally. All the constructs I've shown you in Verilog, put a transistor here, put a gate here, put an expression here, put an assign statement. That has been the biggest thing, the most behavioral thing I've shown you so far, assign statement. But these are concurrent statements. Pretty rough to think about many concurrent statements at the same time, because our brain does not work concurrent. Our brain works sequential or procedural. And then always the statement says, because you guys' brain works like this, okay, so I'm going to offer a statement that mimics this piece of hardware on the outside, but within it, it mimics the way of your thinking. So on the outside, it mimics hardware. On the inside, it mimics our thinking. Okay? Which is human way of thinking. Human way of thinking is, I like to think of something as, if this happens, then I like this to happen. If this happens, I want this to happen. In case, if this is this, I want to do this. Okay? Or I want to repeat something twice. What I'm really talking about is if then else statements, case statements, loop statements, while statements, everything that you haven't seen so far in Verilog, in modules, now you will be seeing in always statements. So for software people, they feel at home inside an always statement. Nevertheless, on the outside of the always statement, everything is still hardware-wise. The entire always appears as a concurrent hardware statement. Okay? So, when there's an event on A or B or C or D or S, flow begins. When the flow begins, if, now here I can write if. Okay? If S equal to tick B 0, 0. Look, for this small example, you're really not going to be seeing any advantage of this always statement over the assign statement. Okay? But then you are seeing procedurally doing something. And we're going to learn the rules, learn the always statement with this small example. And then for larger example, we'll be using this. And there, for larger example, you will be seeing a lot of advantage of using always over the assign statement. If S is this, then W is A. else if S is to tick B01, W is B. Else if S is to tick B10, W is C. Else, I'm not gonna say yeah, I'm assuming everything is good, so I say else W is D. That means if it's not 0, 0, 0, 1, 1, 0, 1, 1, I assume it's 1, 1, and W becomes D. Okay? Like I said, you are not seeing a lot of advantage describing your multiplexer as such, which is the same as this, except that you have if and else's and all that. But then you have learned how to use if-else statements, and you have learned how to describe something procedurally. Now, if you have a case statement, you can put a cases. If certain condition, you have to look at the case statement, and we will be seeing case statements. And in the case statement, put if, then else statement, put loop, and all this. There you can do that. Then you will be seeing advantage. Verilog says, if you're doing something like this, make sure two things happen. One, everything that you're reading, all the inputs, all the conditions, everything that you're reading, like A, B, C, D, and S, they have to appear in the sensitivity list. I call this one Rule 1. Rule 1 says everything appears in the sensitivity list. All ins appear in the sensitivity list. Actually, for the assign statement, I also call the right-hand side signals sensitivity. I say the assign statement is sensitive to these inputs. Actually, for this structure here, this and or structure here, this is sensitive to S, A, and B. Okay? That's always a statement, sensitivity. But then there's something else. Remember what I said about the combinational part. Combinational parts, if there is an event on the input, the output never retains. Maybe the output keeps its old value. The new value, the new value may be the same as the old value, but it never keeps its old value. It never retains the old value. So anytime there's an event, the output will be re-evaluated definitely. Okay, so what I do is, in order to comply with this rule, or comply with this behavior, with this functionality, what I do is I say, well, I want to make sure that no matter how I flow into this, if else, how I flow into this, I want to make sure that my output receives a value no matter what. For this simple problem, I have if else easy. Okay? Therefore, I can just make sure, oh yeah, definitely the output is going to receive some value no matter what. But what if you have ifs inside else's, inside ifs and cases and all that, and then it's not easy to trace the output, and there may be more than one output. It is not easy to trace all the outputs to make sure that they do receive something. I say, instead of doing this, let's right at the very beginning of the always statement, whatever is receiving a value, let's set that value to inactive value. For example, W is 0. And now, if in the if statements, I put a new value on W, that will override this 0 that I have. If I don't override this, well, I am sure that my W is not the same as the old value. I have put a new 0 in it. I call this one rule number 2, output rule. So I have two rules here. One is the input rule, which is sensitivity list, and one is the output rule, which is the setting of the output to its inactive value. This is A, B, C, D, and S. This is input rule, rule 1. Okay, and this is rule 2. Rule 2, or the output rule. So what I'm saying is Verilog gives us a good opportunity to write if then else's. Okay, but then it says if you want to make sure that you don't go wrong using this construct, follow these two rules and then you will be good. Okay, this is a simple multiplexer, and now I'm going to use this same always statement for the ALU that we described in the previous page. One more thing, a very important one. I don't call it a rule, but it's a thing that you have to do. In always a statement, no matter what always a statement, whether it is a sequential circuit, combinational circuit, a small circuit, big circuit, whatever it is, the W output, or anytime you have something on the output, in this case, the W, let me use a color that can distinguish well from the other colors. How about this, maybe? Okay. Anytime you have something on the left-hand side, like W here, like W here, like W here, okay? You want to make sure that your W must be declared as reg, like a variable. And therefore, the change I have to make, if I replace the assign statement with this always a statement, there is one more change I have to make, and that is output reg W. Okay? Just insert the word reg after the output, and then replace the assign here with this always a statement. In Verilog, assign statements, you can order them however you want. The first one is first, the last one can go first, and so on. In always a statement, the same always a statement as a block. This is called a procedural block. As a block, it can move anywhere you want it within the module. But then, inside it, you cannot change things, because on the outside it is concurrent, on the inside is procedural. That covers always the statement. Now let's go into my ALU. I'm going to describe my ALU using an always statement. Okay, now my ALU has a few other things which I'm going to get to, but the bulk of it I'm going to describe this time. Instead of if then else statement, I use a case statement. What are the inputs and the outputs of my ALU? The ALU inputs and outputs are as such. A, B, F, and W. W is the output, right? Okay. I'm going to use an always statement for describing the inside of this. That assigns that always statement must set something into W, and it must set something into the carry. Okay? My input rule says this. All the inputs must appear on the sensitivity list of the always statement. I followed that. My output rule says if your output is W or carry or whatever, make sure never these variables retain their old values, and therefore, just to stay on the safe side, set your outputs to their inactive values as soon as you get into the always statement. That's called the output rule. That sets the always statement. From this point on, I can just do ifs and elses and cases and loops and whatever I like, I can put in here. The easy construct to use here, which I'm showing you here for the first time, is a case statement. Case F means F is the expression. Okay? This expression is compared with these case choices. And then whatever I had here, I'm going to put into this case statement, which is this. So I say, if f is 0, add a and b. But then when I'm adding a and b, remember that or this particular ALU says, well, you also have a carry you have to worry about. And therefore, I put a carry on the left-hand side of W, and then add a and b. Fortunately, I don't have carry. And if I did, that would be no problem. I just add a carry in here. And then if I did, I also had to bring in my carry in the sensitivity list as well. Okay, whatever is in the input has to be there. All right. So that covers choice 0 of the case statement, which is C on the left-hand side of W, making up a 4-bit vector, a 9-bit vector. Okay, W is 8, carry is 1, 9-bit vector is A plus B. Okay, A and B are 8 bits each, and therefore with the carry they make 9 bits. The next one, I'm multiplying A by 2. Well, multiplying A by 2, there is a chance that I get a carry. Okay? There is a chance that I get a carry. And therefore, just like adding A to A, well, there is a possibility of getting a carry. And therefore, that also you put carry on the left-hand side. Next case choice number 2, which is 0, 1, 0. Okay, notice that I'm using decimal numbers. Here, I was using binary numbers fine. Okay. I just like to make it look a little bit more behavioral instead of saying 0, 0, 1, 0, 1, 0, and so on. If the function is 2, then W is the greater of A and B. That means if A is greater than B, let me show each one of those. If A is greater than B, then A goes on the output, otherwise B goes on the output. If case is 3, I'm performing bitwise and then putting it on W. If case choice is 5, that means function is 5. I'm doing 2's complement of A. 2's complement of A means that it takes A, complements it, adds a 1 to it, right? 2's complement means this. Whatever A is complemented, add a 1 to it, and that becomes the W for function 5, as you are seeing over here, 1, 0, 1. Function 6, easy. A goes on W. Function 7, complement of A goes on W, and then I have a default. Default means just in case something goes wrong, just in case none of those match. Okay, just in case one of your inputs is open or has an X value on it or something like that, then put a default there so that at least you just don't leave your output unchanged if a bad situation happens. See, if I don't put the default, it doesn't match any of these, that means one of your functions has a function bits, has an X on it, then you get to this point, none of the cases up there match, and therefore, if I don't put the default, the output retains its old value. That's a bad thing. And therefore, I put the default, W is 0. If bad things happen, W becomes 0. And then I put end case, and then I put end to end the begin that I have here. Okay, that's an always statement. I block it, it becomes a concurrent statement. Now I can take this always and put it there, put it there, put it anywhere I want of my choice. I'm not done with the with the ALU yet. My ALU, remember, the red here is the output rule. The green here is the input rule. And then I also used this color, whatever it is, okay, to indicate that my output in an always statement has to be reg. And therefore, my output here, the W output is reg, because W is used on the left-hand side in an always block. C is reg because C is used to carry in an always statement on the left-hand side. Here, you see that, right? C is used here, C is used here, W is used here, W is used here. And therefore, when I put this block in an ALU, I want to make sure the declarations are reg, at least for the variables in this always statement. I'll show you the rest of them in a few minutes. Let me say something. Remember I said that I just indiscriminately set all your outputs to the inactive values and then selectively set them to whatever value they're supposed to. Okay, and then I say to stay on the safe side, put all zeros into all of them right at the very beginning. And then I also showed you here that in this previous example that if you didn't put the W equal to 0, that wouldn't matter because you're setting it to all new values anyway. That situation doesn't exist here because in two of the case choices, number 0 and number 1, C is receiving a value. In the rest of them, C is not receiving a value. And therefore, if I had not put C equal to 0, and if my case was, for example, number 4 for ORing, C would retain its old value. This is not what I expect from combinational circuits. And therefore, to stay on the safe side, I set W to 0, C to 0. C proves to be useful in this case. All right. I also said ALUs have flags, C, V, Z, N. I covered the Z flag. Let's cover the overflow flag. What I have is this block here, this always block here, A, B, and F. And then the output is W. This is this always block. Okay, is this. Now I want to set the overflow flag. See, the overflow flag, remember the overflow flag. The overflow flag is set because of a bit of A, a bit of B, and the overflow, I don't say overflow unless I'm adding, right? If I'm not adding, or if I'm not multiplying by 2, meaning shifting 2, there is no point in saying here is an overflow. Okay? And therefore function also participates in this. What else participates in this block? Something else that participates in this block is, remember when we did the overflow, we also looked at the output of the add. The output of the add here is on W, and therefore W is also an input to the block calculating the overflow. And therefore, this is the output of the output always. Output always. This one. This one is the overflow. Okay. And then I'm also writing an always statement, and therefore W, A, B, and F have to be included here in the sensitivity list. So once again, the input rule says that A, B, F, and W have to be here, which is this. The output rule says that no matter how you flow into this, the output, which in this case is V, has to receive a value. In the above, I was conservative and set my W and C to inactive values. Here, this is a just simple case statement, so let's not be that conservative. I will make sure that V receives a value anyway. Okay, it wouldn't make a bit of difference if you say V equal to 0. Okay. And if you want to stay on the conservative side, do so. Let's look at this always statement. It says if F is 0, 0, 0, that means you're adding. Okay? And if you are adding, and A is A7 is 1, B7 is 1, W7 is 0. Negative, negative, positive result. Positive, positive, negative result. If any of these two cases happen, your overflow flag is set to 1. Okay? If you're shifting to the left, that's also an overflow if what? If see here, you're shifting to the left. This is my original A. Okay, and you're shifting. This is a negative number. You're shifting to the left. This is also a negative number, so you're fine. You're fine because the two bits 7 and 6 were the same. Okay, this is before shifting. This is after shifting. But then I don't have to actually look at the after shifting. I can just look at A7 and 6. If they're the same, I know after shifting the sign bit will be the same as the before shifting. If they're different, that means, it's a negative. After shifting, it's going to be positive, or no, it's positive. After shifting is going to be negative. Therefore, that's overflow. And therefore, all I do is this. I say overflow becomes 1 if A7 and A6 are different. That's A7 before shifting. A7 and A6 are different. Okay? This is the A. This is A shifted to the left one place. Which goes in W. Okay? I could do shifted or I could do curly bracket, doesn't matter. Shifting is like taking A, put a 0, and then move it to the left. And therefore, this XOR here tells me if in case of shifting, I'm going to get an overflow. So I get two cases of overflow, one adding when sign bit of the result and sign bit of two operands are different. That's one case. The other case is if the two bits next to each other of A that is being shifted to the left, they're different. That's also an overflow. I could do this overflow using an assign statement. Actually, I could do the whole thing using an assign statement. But then I'm using two always statements. And then V, which is the left-hand side in an always block, is also declared as reg. Look up here. I'm also setting the 0 flag and negative flag. I'm using an assign statement for the negative flag. I'm using an assign statement for the 0 flag. Negative flag is 1 when W bit 7 is 1, obviously. Okay. 0 if all W is 0, that means OR reduction of W, OR reduction. This symbol is reduction. If OR is used just by itself, is reduction. Okay, and OR reduction means that these bits of W are all OR together, but then I do a tilde here. That means this is NOR reduction. And if NOR reduction is 1, it means that Z is 1. See, this is the same thing. So I could write this instead of this, which is implying this. I could write and tilde W. Complement all bits of it, but then they AND them together. That means I'm doing AND reduction of complement of bits of W. These two. That's my ALU, and this is the ALU using an assign statement. I'm going to do a simple case study, just to show you some simulation. Next.